So let me welcome everyone to our seminar of mathematical physics. And our speaker today is Filip Moučka, who is a PhD student at Czech Technical University and also at the Autonomous University of Barcelona. And he's going to tell us about a symmetric cousin of Poisson geometry.
Thank you, Frederick, for this introduction. So I'm going to tell you something about new geometric structures that we call symmetric Poisson structures. But let me start with motivation, which is actually classical Poisson. So motivation for us is this classical arrow that sorry. You start with a symplectic manifold, and what can you do is, because you have a two form and this two form is not a general, you can always take its inverse. And its inverse is actually skew symmetric vector field. And because this two form is also closed, you can try to phrase this closeness in terms of this inverse. It turns out that it's actually possible, and you can write a condition and redefine what symplectic structure, symplectic manifold is in terms of. Okay, this bracket here, it's a scalar bracket. I will tell you in more detail what that means if you haven't seen it before. But this is the important arrow which we will actually generalize, which is the motivation towards. And once you have this, you can simply generalize symplectic by dropping this non-degeneracy condition and define what Poisson structure is. Poisson structure is straightforward generalization. It's a vector field such that it satisfies this kind of field. Okay. And when you see this, there's kind of naive but actually natural question which you can think about, and it's okay. I don't start with symplectic manifold, but I start with a pseudo-Riemannian manifold. And now, I have again non-degenerate object. So what can I do? I can take the inverse. When I take the inverse, I have something which is in second symmetric power of the tangent bundle. So I call this object symmetric vector field. And just that's the notational thing. I will not use the notation, but this will denote the space of all symmetric multi-vector fields. Okay, but then there's kind of question is that what's kind of analog of this thing here? Because it's not so straightforward now because there's no like closeness here. There's the concept of longitudinal connection or whatever, but it's not so straightforward. It's kind of what to put here as extra condition that would somehow capture some interesting geometry. And our approach to this question is somehow mimic the Poisson point of view and develop these new geometry. Okay, so this is the motivation. Hope it's clear what we are trying to do, and let me now go to the definition of like this degenerate way of treats like pseudo-Riemannian.
So maybe just out of curiosity, should it lead to anything interesting to the post-flatness of the metric, like as an analog of integrability?
Well, then you can do it, of course, but then how would you phrase flatness when this is not non-degenerate because you don't have longitudinal connection anymore? You know, like when I have like just arbitrary symmetric vector field, I can't say what's flatness because I don't have longitudinal connection.
I see. So it doesn't lead to anything like interesting.
It can't be generalized. It's just whatever it is. Thank you. Okay, so this is scalar bracket. So there are like several equivalent definitions how we can define it. Most nature of this for me is via the derived brackets construction. So to do it, well, you want to define a bracket on all like skew symmetric multivector fields. So the first thing you do, you can embed your skew symmetric multivector fields to a space in which you can treat them in a better way. This for this purpose. And how you do it? Well, like this canonical identification via contraction, because to any skew-symmetric multi-vector field, you can assign an endomorphism of differential forms by construction. And then you define your Scouten brackets. Okay, I have two multi-vector fields. I have X and Y. I pair them together with their differential and graded commutators. Consider this expression, and okay, if you do the calculations, then you realize, okay, this defines a unique multi-vector field, and okay, this is the Scouten one of them. Okay, and I said that our strategy is to mimic really Poisson geometry. So the first step is somehow to get analog of this Scouten brackets, right? So the first step here was to identify multivectors with some endomorphisms. So we can do the same for symmetric games. So we can embed symmetric multivectors to endomorphisms, but not of differential forms anymore, but of symmetric forms. Sections of symmetric powers of the potential one. That's what can you do for sure. But then there's kind of first obstacle, and the obstacle is that okay, you could try to be also like great community. And the obstacle is that okay, you need some operator like zero derivative, right? So what we have to do somehow is to find an analog of the differential which would live on symmetric forms rather than different. So if you recall the definition of the differential, it's axiomatic definition. Actually, the usual definition is axiomatic, and so let me try to mimic it. So what we would like to have, we would like to have degree one operator here, and we would like to have it compatible with the algebra structure we have on the space. So we want it to be a derivation of the symmetric algebra. And moreover, one of the axioms for the RAM is that it acts in a nice way on functions. You want this to be specified. Okay? You can consider this space. The analog properties we would like to have for our analog of the differential. Okay, just also squaring to zero. I will comment on this in a minute. But okay, let me put it in this way for the moment. And okay, the first question is whether this has some element, whether it's empty or not. It's not empty, because what you can do, you can always take affine connection. And for affine connection, I can define object link together. I usually denoted by this nabla S, and it acts on like symmetric form. The following formula. So first you increase the b by 1 using the connection, then you symmetrize it because you want to obtain a symmetric form, and then there's like an integer per factor which ensures that you really have derivation of your algebra. Okay, so this gives me sets of the connections on manifolds. Kind of map here, right? And what you can check, it requires some calculation, is that this map is actually surjective. Which is nice, because now we know that okay, when you want to have a replacement of exterior derivative, this is the only possible thing. Maybe it's torsion free. Yeah, that's what I want to say. If it's torsion free, it becomes budget. If it's torsion free, and it's like isomorphism of affine spaces. The important thing is that these are the only candidates for replacing the Roche differential on this. Great. And now it's very easy to define the symmetric Scouten brackets. What you do, just kind of mimic this trick which we did here. So we define symmetric Scouten brackets. Good. So it's brackets. What we would denote by this symbol here, which comes to S, and it takes two symmetric multivectors. Another symmetric multivector, and it's given by the following formula. So I take contraction by a symmetric multivector, I pair it with the symmetric derivative, another one, and again check that it defines a unique symmetric multivector.
Yeah, but it does not get to zero, right? So it's correct.
Yes, but I mentioned that I will say something about squaring to zero. Okay, so if we put it here, if we put squaring to zero, then it's not possible actually. It's not possible. Maybe it is nice. Yeah, like there's no object that will satisfy these properties and put square to zero. So now you may say, okay, so perhaps I can simplify this and square to zero, but it's possible, but the only object is zero. Interesting, right? So this is basically not possible when you want to work with symmetric object. Good. So we have this bracket, and now just to have a idea how this symmetric Scopian bracket looks, let me specify it for vector fields. Yeah, is where it is expression because it's just like symmetric part of your collection. And it will be useful like when we talk about symmetric Poisson structures. Great, so this is symmetric Scopian bracket, and now it's very easy to define what symmetric Poisson structure is because we just mimic the definition. That's it. Definition, symmetric Poisson structure. For us, is a pair of eta lambda, where this guy is just symmetric vector field, and this thing here is total connection. And restrict to total connection without loss of generality when we work with symmetric Scopian bracket. Such that this condition here is this is symmetric Poisson. Okay, so we have a definition. We can arrive to it in some natural way, let's say. And now it's good to somehow check whether we are getting something interesting, right? So the first check is what happens in the non-degenerate case.
Are they not to go for this thing, right? Because it's not B, it's not super B, right? So that's not just
It's commutative brackets and
cannot be invited to the sound.
yeah, I don't think so actually, because it's really a different story as probably as Calvin, because it's really commutative in all degrees. Okay, it's compatible with the
But still. So it's not a part of anything.
sorry,
It's not a part of any kind of leak structure.
I don't think so either, because there's no even like for this bracket on vector fields, there's no way like analog of Jacobian.
It seems that at least for the vector fields, it satisfies some kind of Leibniz rule. That's
Yeah,
like-
there's like this, yeah, it's compatible with symmetric product.
But you
It's
say-
by derivation.
Yeah, it's derivation in both.
But that's all. It's much more.
Good. So for theta non-degenerate, what I can do, well, I can take its inverse and I get a zero Riemann equation. Right. And then the question is whether I can rephrase this condition on the bivector in terms of this metric. Can actually, and what's the condition is that this metric is closed with respect to our symmetric derivative. And this condition actually has a name in the literature. It means that G is appealing tensor. So these are particularly interesting because they define like conserved quantity along geodesics. Corresponding connection. Good. So now having this, we know that actually any pseudo-Riemannian metric can be seen as a symmetric Poisson structure. Because what can I do? I can take the inverse of my metric and deal with a connection, and these are actually inside symmetric Poisson, which is good because okay, this is what we wanted, right? We wanted to somehow find a theory that would extend pseudo-Riemannian geometry in some natural way. So very successful, and moreover, this gives you that every manifold admits a symmetric Poisson structure because every manifold admits every manifold. It is the similar claim as is in Poisson geometry, but in Poisson geometry the argument is quite different because the argument is that zero vectors in every manifold.
You can take a zero.
Yeah, that's okay. You can take a zero, and there you get another class of symmetric Poisson structures, and these are like closure-free connections. When theta is zero, this condition here is automatically satisfied, so any connection can be seen as a symmetric Poisson structure. Yes.
This is typically when we think about performance Poisson manifolds and think about symplectically expressed.
Yes, we will have something like that.
So it's possible to get symplectic leaps.
Not symplectic, but pseudo-Riemannians.
Should they?
Yeah, I will get there.
Okay.
So we have justified the non-determinate case, and another question is like whether these are all symmetric Poisson structure, right? Because if there's equality, then like our theory is kind of not very interesting, right? And there's equality, but if dimension of the manifold is one, we're restricted, and if you go higher, then there's the inclusion is really strict. So it offers some new examples, new geometric structures, and yeah, following what Margot asked, into the third part of my talk, and it's geometric interpretation.
I will still like to ask, if you are given a symmetric Poisson structure, can you recognize it comes from a pseudo-Riemannian metric by some kind of intrinsic way instead of just inverting?
Okay, so I mean, I start with like some theta, and
Yeah.
try to recognize whether it's coming from pseudo-Riemannian metric, right?
Yeah.
Well, if it's non-degenerate, then it's coming from pseudo-Riemannian metric.
What about the connection?
Yeah, so this is like canonical, so.
Yeah.
So
Okay.
if I start with theta and nabla, and my theta is non-degenerate, and okay, so if it's non-degenerate, then I know it's a symmetric Poisson structure, and then I know that this is necessarily satisfied.
But so you will just have to check that nabla is the Levi-Civita if you wanted to check it comes from.
Yes, yeah, okay. Yeah. If you want to like recognize these, then you have to check that this.
Yeah. And there is no direct way, just like staying in terms of nabla and eta.
Well, yeah,
So,
we
sorry.
will have some way. I will get there, so I can comment.
Okay. Thank you.
Okay, so geometric interpretation. So, okay, if you are outside of these spaces, then it makes sense to introduce some associated quantities. And the first one is characteristic distribution. So what I can always do when I have my theta, I don't even need my symmetric Poisson structure, is to look at it as a map from cotangent bundle to tangent bundle, right? And it defines me a distribution. The distribution actually can be singular. And when it's singular, it makes sense to introduce another quantity, and it's the characteristic module. In that case, these two. In the singular case, these two things will carry a different piece of information. So what's the characteristic module? Well, it's a similar to characteristic distribution, but you look at it as a map from one forms to vector fields rather than a map between vendors. So some submodule of module of vector fields. And what's good about this module is that it's well behaved in the sense that it's local and locally finitely generated, so you can apply all the theory of singular distribution if it's involved. Okay, and now this is for arbitrary symmetric bivector field, but what happens when I have in my hands symmetric Poisson structure? So I have theta nabla symmetric Poisson. Then it's not big surprise probably, but what I get is that this module here is involutive, but not with respect to the Lie brackets, with respect to the symmetric brackets. This bracket. We will see that this also has a geometric definition. What's important is that in general it's not involutive. It's also not big surprise. Not like involved for the bracket. But we can, under some condition, make it involutive. So let me make a comment on some more or less notational thing. So when I have theta, no symmetric Poisson necessarily, I can always assign to it a bracket on functions. In the same way as you do it for Poisson structures, right? So some f g I assign to theta df dg, particular functions, and I have also a way how to create a vector fields out of functions. So I have gradients now. It's just simply given by here. So I have these two things, and here. And what's is for me surprising is that this condition here is not coming from the because in classical Poisson geometry you have this condition here satisfied that like this characteristic module is involved for the Lie bracket, and it's coming actually from the fact that the map that assigns a Hamiltonian vector field is an algebra morphism. But in this case, gradient is not algebra. Okay, this is not necessarily satisfied. Gradient does not intertwine brackets. So now, if I turn out the rise board, if there are some questions, just ask.
Just a stupid question.
Sure.
So if you start with G, take its inverse,
Yes.
and as an affine connection, you take the one induced by G. What's your symmetric Poisson?
You mean, okay, so I start with metric, I take the inverse and a symmetric bivector field, and then you take the original connection.
Yes.
Then my symmetric Poisson structure is G inverse and the original.
Thomas, I was sleeping. Sorry for that.
No, fine.
Why you need torsion?
Well, I don't need it, but it's like the Dalton's generality, and it's easier to work with torsion-free connections. Because we had this one-to-one correspondence between like these derivations of symmetric algebra satisfying blah blah blah. That's okay. And
So sorry, stupid question. So of course, all the connections are related by one tensor.
yes,
There is one tensor between two of them.
yes,
So can you specifically calculate how does the
yes.
symmetric Poisson bracket change?
Yeah.
And
Exactly. Because they, like the torsion-free connection differs by like section of sin to T star m tensor Tm. Yeah, you can Is that a nice formula or something nice? I think, yeah, honestly, I didn't try to do it because I don't think that it would help to anything what we want to do. But
The construct is not like as your good motion just disappear.
yes, yes, yeah, you see only the torsion part of the connection. Okay, and it's kind of surprising, at least for me, is that if this is satisfied, okay, so I have this condition, then it's surprisingly important. So it gives me a condition, which is kind of funny because I force like this involutivity with respect to the symmetric bracket, but it really gives me that okay, this characteristic module is involutive. And not only that, it also gives me that I have a symmetric Poisson structure. That gives me kind of both properties. So it's a stronger condition, and yeah, Kianchi asked like the writing that like if these two Riemannian metrics somehow intrinsically, and it's precisely this condition when my theta is non-degenerate, then this exactly wants to be here. Good. So now we have several conditions, and what we can do, we can kind of build a hierarchy of integrability conditions. So we have symmetric Poisson as the most relaxed one. Then what we can do, we can put like involutive symmetric Poisson, because like all of these will have really different geometric. Okay, these are these two conditions. And then we can have something we call strong symmetric Poisson. And it's the condition with the gradient. So we have the hierarchy, and one of the fundamental questions structurally in our theory is whether these equations are strict. And the answer is yes, equations are strict. And okay, each of these classes with a differential behavior. So let me now continue with the geometric interpretation.
Sorry, one question. On the other board, it's written that symmetric Poisson implies that it's involutive, but I missed something
Yeah, but
probably
it's
there.
involutive respect to this bracket with S, so it's a different bracket.
But there is an empirical.
Ah, okay, so there is a mistake. Sorry.
Okay, thank you very much.
Sorry. Yeah. Because that would not be so surprising. Yeah. Okay, so the easiest case when you can really find the geometric interpretation of our structures is the regular case. Means that like our characteristic distribution has the same rank at every point. And for that, let me recall the definition. So when I have a nabla on my manifold, I have a connection. I can decide whether my distribution is so-called geometrically invariant. And what does it mean? Well, it's already saying that if it's geodesic invariant for every geodesic with respect to this connection we have, I have the following property that it's tangent at a point to my distribution. It stays tangent to the distribution like forever. So, and yeah, this definition can be set not only for regular distribution, but for any distribution. It's still like a definition. To have some to like see like what are these distributions, how do they look like? Let me give you an example. So this example, I take the plane with Euclidean connection, and okay, the example of this geodesic invariant distribution is for easy. It's just distribution like it's integrable. It's true that this distribution do not need to be integrable, but okay, like it's easier to draw integrable distribution than non-integrable distribution. Okay, so this is geodesic invariant. Right? Because geodesic hits the distribution, it stays in the distribution. What's not geodesically invariant, for example, is it's this distribution, right? This is not geometric invariant. Because okay, I have a line, straight line, it hits the circle, it leads the circle immediately. So geometric invariant, and there's that intermediate notion, which is good to introduce when you work with singular distributions, and it's like locally geometrically invariant. Example of this is just this kind of behavior, right? So my line, it's a distribution. Here and it stays in the distribution on a neighborhood, but it doesn't stay in the distribution forever. Different notions. Okay, and how this notion relates to symmetric Poisson geometry? Well, there's a theorem not proven by us, but proven by Andrew Lewis from Queen's University in 1980. Which says that a regular distribution delta is geodesically invariant, not locally, but geodesically invariant. Its space of sections is preserved by this symmetric brackets of vector fields. Again, this has like immediate consequence for our theory because it tells you that okay, when I have symmetric Poisson, then this guy is geodesically invariant. Great. So this is regular case. Singular case is much more difficult because you can't really adapt this theorem because it really relies on the regularity. So we have to develop some of our own tools, but before going to general singular case, let me tell you something about like this. Here, all of this.
Was this person introduced the symmetric graphic or?
Yes, that's yes on vector fields. Of course.
Use the writing. It should be one paper.
So the inverted case. So now we are finally getting to predictions. So one thing, the introductory remark, is that okay, we have this distribution, we have this module, but every theta also kind of gives you the characteristic metric. Doesn't need to be symmetric Poisson. What's the characteristic metric? Well, it's very many metric. But it's like pointwise metric. It's usually denoted by this, and it's really strict on along the distribution. Right, so it's not on the entire tangent space. It's really metric on the distribution, and it's given by a simple formula. Example. Just okay. So it gives you pointwise metric that can't measure like all vectors, but vectors that are in the distribution. Good. And now for the inverted case, there's very nice things because when this is inverted, you have a Poisson. And then I already said this, I have a singular relation.
So this characteristic metric is something like
Like,
analog of symplectic for non-symplectic leaves.
yes, precisely. But yeah, for symplectic leaves, you can really like get like honest symplectic structure on submanifold here, so that like quantized object. But in the important case, you know. Okay, this arrow looks like very easy, but it's actually hard. And there's work by Stefan Sussman and like many other people like studying this incorporation and proving really this kind of error, like in general, not for symmetric Poisson. Yeah, I can build on their work, and now it becomes very easy.
Classification of singularity allowed singularities.
Sorry.
Is there like a classification of allowed singularities?
Well, just yeah. I somehow not like precise theorem, but I guess you mean like whether because there are like type of singularities, like one of them is like this, but
Yes.
and yeah. So somehow like in examples we have like we are able to get our singularities of this form. Yeah, it's kind of open question whether we can get some of these singularities. Okay, so we have this involutive, we have the singular correlation. So we have leads, and for every lead, what I get is honest metric, and then pseudo remaining metric on a lead. But that's not all. I have also a torsion connection coming from number. Some data induced on the lead. Well, this metric is just given by like putting together these pointwise metrics, and this is just given by the restriction of the connection. It's not like something you can do in general, that you can restrict your connection on a submanifold, but in symmetric Poisson we can do it. Okay, and then we have a theorem which describes the relative geometry of this involved symmetric Poisson structure. And the theorem is saying that the operation produced by Isha Nabla is totally geodesic, which means that every leaf is a totally geodesic submanifold. And yeah, being totally geodesic submanifold is really analogous to like being geodesic invariant distribution, which just means that your geodesic hits the leaf and stays in the leaf on neighborhood. Then it can leave or it can stay.
So it's basically like a globally less minimized.
Well, yeah, somehow it's totally geodesic, but not because what you are referring to is that when I have a global metric, right? So my minimum, I don't have global metric on minimum. So it's a generalization because I have just connection, so I have to express it in terms of. Okay, and that's not all because I have also the characteristic metric. Moreover, for every B, this GM is scaling for the leaf connection. So okay, one could think of that perhaps okay these torsion-free connections would be like the connection of the characteristic matrix. Right? It would be nice, and this happens if my symmetric Poisson structure is strong. So theta level strong, then my line is really Levitt-Rita for GM. Okay, so I mean, I think that this theorem kind of shines some light to geometric problem. Imagine that you have like a foliation, you have a metric on each leaf, and you are wondering whether there is a connection, global one, that really restricts to the connection on every leaf, such that it's a Levitt-Rita connection. And we know that when foliation is coming from I vector, from symmetric Poisson, then
Okay, so I guess the other direction is not true. So you could kind of measure the non-strongness by calculating the torsion of this number line for each leaf.
well, the torsion is zero always.
No, but you are saying that if your strong, if your symmetric Poisson structure is
strong that I
Strong, that is symmetric. I'm asking whether
you-
the correlation sort of
I think that it is, but I
this would be because this would give you nice kind of geometrical understanding.
Yeah.
What's the how to measure how
Yeah.
how not strong it is.
yeah I think that it's actually true, but I don't even think that it's hard to prove it, but I'm really. Okay. Great. So this is intuitive, and now comes the hardest part, and it's general case. Something which is hard because you can't build on work of anyone else, right? Because for regular case we used Luis, for intuitive case we used Stefan, Sussman, and people, but now we are alone somehow. And for this path, I need to take a little detour to something which is at first glance totally unrelated, but actually very related. And it's the Peterson-Walker method. So what's Peterson-Walker method? Well, it's a concept which is quite old, but not very well known, as far as I know. And is due to Peterson and Walker, surprisingly, from 1952. And it's a kind of way how to, from a connection on a manifold, build a metric. So what can you do? Well, so it's kind of inverse to like Milovic-Kita connection concept, right? In metric, we build a connection, and she has connection, we build a metric. Okay, so I have connection on M, and when I have a connection on M, this gives me, so I can take the dual connection is a vector bundle connection on the cotangent bundle. It gives me the composition of this tangent bundle to horizontal and vertical subbundle. And now this guy can be canonically identified with a pullback bundle. Then I'll become a projection by R. And this is nothing else than Dm plus d star, so the generalized tangent bundle. And what else do I have when I have a connection on M? Well, I have a horizontal link. So I have a way how to create a vector fields on the cotangent bundle out of the vector fields on the base. But I have also vertical width. It's kind of hidden here in this isomorphism. It's just pullback section and the identification which is here. So I can also create vector fields into one forms. Right. And now having this, I can introduce the Peterson-Walker metric. How I do it? Well, because like images of these two maps will generate all vector fields on the cotangent bundle. I can prescribe my metric only on them. And I want to find somehow the function on the cotangent bundle out of this data. And there's a canonical way how to do it. Take Uber. And then you take the function y. You have ever seen general geometry, these guys probably familiar to you because it's kind of the key object of the whole theory, and everything basically flows from this guy in general geometry. Use it to define your form correctly, then everything is right. Okay.
Why do you need to project to pull it back by projection?
Because I need a functional potential bundle. This gives me a function on it.
So it's still
In coordinates is the same.
okay.
Good. So we have a well-defined metric. Thinking that this is called fine. And let me tell you more about the metric, its properties, and then I will tell you how it relates to symmetric Poisson geometry. And their original definition was kind of in coordinates, and their motivation was somehow to maybe want to study manifolds with connections, but there is much more known about manifolds with metrics, so we kind of push all problems to, for example, instead of affine vector fields, you can study like killing vector fields or something like that. Motivation. Yes. Sorry. Yes. So what are properties of this metric? Oh, no, I think I lost my track.
Maybe it's the on top of
Right. Thanks.
Yeah.
Okay, so I have a report now, and what are like really basic properties? Okay, so first thing, it's spread signature. Not hard to guess because okay, the pairing there is also split signature because, for example, tangent one is the Lagrangian, so that's to be split signature. Second thing is that it's I already told you this. It depends on that one. Like it really remembers the connection because there are construction using connections, and then the final object really doesn't remember anything about the connection, but this one does. And finally, you can kind of see it as an analog of canonical symplectic structure on the tangent one. Okay, how you usually define canonical symplectic structure as a stereo derivative of canonical one form. And okay, you can also see G Nabla, the Peterson-Walker metric is symmetric derivative of canonical one. In some sense, because remember this connection is on N, it's not on cotangent function, so you have to lift it and then apply this. In some sense, it's true. Great. The last thing I want to tell you about the Peterson-Walker metric before going to symmetric Poisson. Geometry is a theorem which I find.
Sorry, did you require the connection in the beginning to be torsion-free, or is it that
It's again the opposite geometry. If you don't require it to be torsion-free,
it's only the torsion?
versus torsion-free the connection, the construction. Okay, there's theorem which originally actually was proved by and Shilham, Jardnik, and some other people, 5 authors. And then we kind of rediscovered it and add some new things. Okay, it's like just calculation of the Lie algebra of the vector fields of this metric. So the Lie algebra of filling vector fields of G Nabla is actually a very nice form because it can be expressed in terms of object living on the base. So, and moreover, it's kind of the extra piece which we have added is that it has the natural grading. The grading is concentrated in these degrees. It's something called regraded algebra. It's according to unknown. Okay, so what are the components? So first of all, you can take the vertical lifts of one forms, and then it becomes a killing vector field if it's killing one tensor. So the original collection would be Levichita, these are just killing vector fields of the metric. In this degree is one. Then you can take the complete width of a vector field. Someone is interested in the definition, I can give the definition, but it's some kind of leaf which is canonical. And if my vector field on the base is affine, it lifts to a killing vector field degree 0. And then there's the most interesting piece, which is degree 1 killing vector fields. And surprisingly, we started with Poisson structures, and here appears Poisson structures. Because okay, these are like skew symmetric bivectors satisfying 2 conditions. I will not tell you precisely what the conditions are because it's not very important for this talk. But okay, this means that phi is parallel, but this gives you that phi is classical Poisson structure. And there's some condition on the curvature, so depending on phi. And then, okay, you can lift it to a vector field on the cotangent bundle, and it becomes killing vector field for the metric. And this actually also has a name. We found that it's called contravariant. geodesic spray over Poisson form, which is used when on marbles to somehow prove like symplectic realizations of Poisson structures. Great. So this was about the Petersen-Walker method. I hope you now have a better feeling what the object is.
So it's algebra is one thing also known in the algebra like S01 and +1.
Well, I guess
what you have naming, so they are fully classified in their symbol. Be that simple.
okay. Yeah, I don't know, but I guess it really depends what you have here in the middle. This is kind of non-trivial piece because these are Hungarian because of the grading.
And the values are adaptive.
I might.
Is it infinite dimensional?
No, it's fine. It's the algebra of getting back to this is always fine.
And all because it's really metric.
Yeah, it's similar. But on a bigger level. Yeah, I think that this piece is interesting because these you can kind of guess from trying geometry, right? You have like symmetry is given by vector fields in one part, but then like this mysterious piece appears, which I don't really know why, but it does. You know how much time do I have to prepare? That's 9 minutes. So I will not show you any examples. Okay, so relation to Petersen-Walker symmetric Poisson. Okay, so what you can do once you have this metric, you can study gradient flow of a function of a tangent bundle, right? That's what you can do. And actually, when I start with theta and nabla, and I don't require it to be symmetric Poisson, I just forget about all symmetric Poisson I've seen. Just start with this data, then, okay, this gives me the Petersen-Walker metric. And this guy actually gives me a function of the cotangent bundle, right? So vertical length of a vector field, okay, I can express it explicitly. So it eats one form and produce a number, and the number is, you can even write it in coordinates if you prefer coordinates, just like quadratic polynomial in hypercoordinates. Okay, and what I can do, I can really calculate like integral perfect equation for gradient of this function with respect to this metric, right? And the surprising thing is that, okay, this curve on the cotangent bundle is integral curve of these vector fields. It is, and I know that, okay, hopefully at least they always exist, right? When I have some initial condition, then I have necessary condition to be satisfied and can be phrased in this way. And there something appears. And what was gamma? Gamma is just projection of my curve on the cotangent bundle to the base. So we see that this symmetric vector field actually is an abstraction for gamma being geodesic. And you can really use this, and also the local existence of integral curves, which is always guaranteed, to prove the theorem, which tells you what's the geometry hidden by like encoded by a generic symmetric Poisson fracture. Because putting these two things together, you can prove that the characteristic distribution of any symmetric Poisson is well-coded geodesic environment. So you kind of use really strange tools, but you can prove it then very easily. Once you have the Petersen-Walker metric, it's just really the existence of focal formations. Okay, that's not all because we have always the characteristic metric, right? And so what can we say about the characteristic metric? About the distribution? Just like this.
may I ask you, the last theorem is connected, you mentioned, last theorem is mentioned to tangent, to cotangent, or?
Sorry.
On the situation of tangent bundle?
No, it's completely general. It's completely general. I have manifold like symmetric Poisson structure, and I know like the geometric properties of the characteristic distribution. Okay, and you know that in pseudo-Riemann geometry there's very known property that when I have a geodesic, then like its square speed is conserved along the geodesic. And in symmetric Poisson geometry we have a similar. It's kind of continuation of the theorem. So when I have a curve on the base such that there exists kind of lift of the curve, potential bundle, which I mean by lift, well, that it's powered by this theta, so gives me the velocity. I have some curve that I can really measure by my pointwise metric. It's not real metric. Then this function is constant in gamma integers. Generalization of this well-known property. Okay, I guess my time is right. I can continue. I can tell you about examples because okay, this is the theory. We explain the geometry, which is written in these new geometric structures. But what's important is to have some interesting examples. And I guess I will just skip to one example.
Can I ask before you raise?
Yeah, sure.
I don't understand. This
What?
this nabla,
Yes.
you are derivating this gamma velocity. And you have this bracket between theta and theta.
Yes.
It's a symmetric bracket that you define.
Yes.
But then, what is this?
Yeah, it's like construction by this curve. So you can insert like one force to it, right? Because it's a straight vector. It's like 2 times contract.
It's iota.
Right.
So the point is, it's an integral curve of this distribution, given by the Poisson structures.
Yes.
Then the gammas are something like half, not geodesic, but already spaces.
Well, in general, when I have a curve on the tangent bundle, I can always project it to the base, and I get the curve on the base manifold.
But in general, they are not geodesic. Because,
Yeah,
it's not zero.
Yeah, it's true. But if you have a symmetric Poisson structure, then they are geodesic. Just integral curve. Yeah, that's true. Yeah, correct. So this is really the obstruction. So you can even like come to the definition of the symmetric Poisson geometry from this like dynamical viewpoint that you see it as obstruction of something. So the first interesting example, which is quite different from what you have in Poisson geometry, is that you can really capture non-integrable distributions. And in particular, you can capture like the contact distributions. So one, so I have a Lie group, Heisenberg 3-dimensional group. Then there are 3 generators of flat invariant vector fields that define this permutation relations. And what I can do, I can consider such theta, which is just very easy. This. And I can equip it with a connection, because on the Lie group, I have also like always canonical torsion free connection, right? And these two give me the symmetric Poisson structure. What's kind of important is that this image of theta is the standard contact distribution on R3. And moreover, the metric you get along the distribution is the standard structure. This is the first interesting example, and then yeah, I don't know how much time. So another interesting examples can be found when you go to linear case. That's the case when your manifold is the dual of a finite dimensional real vector space. Because okay, I will now skip some details, but you can somehow identify these with some algebras. These algebras were defined by the Tripur and Alisafilowski in 2014. Yeah, they are called Jacobian algebras. And what are these Jacobian algebras? Well, they are just commutative algebras satisfying cyclic Jacobian indices. And in particular, these algebras are factor cases of the other algebras. That's why you're doing this. And okay, then what can you do once you have this result is that you can bring a lot of examples from papers in algebra. You just take Jacobian algebra and assign to it corresponding symmetric Poisson structure. And what's good about this paper is that they give a classification. So you know that up to dimension 4, all Jacobian algebras are associative. And from yes, sorry.
So this is like analog of linear Poisson structure.
Yes, and the algebra.
Symmetry algebra.
Yes, precisely. And then, like for the connection, you can always use Euclidean connection, so you can get rid of this connection. And up to dimension 4, all algebras are associative, which in terms of symmetric Poisson geometry means that they are strong symmetric Poisson structures. So thank you. Euclidean connection really restricts to the Levi-Civita connection, the metric on the leaves. But in dimension 5, there's like probably our most interesting example. Okay, I will just write the formula and then I guess I will just. And okay, so you take the Jacobian algebra and you write down the corresponding symmetric bivector field. So you just put the formula. So it's not like something really easy, like the first ones. So we have this symmetric bivector field, and what's interesting about it is that it's involutive, but by any choice of a connection, it can't be made strong. So you can't really find for this. This gives you foliation by metrics, but you can't really find a connection that restricts to the Levi-Civita connection on the leaves. And okay, the leaves are of dimension 0 to 1, 2, and 4. These leaves are flat, so the Euclidean connection really restricts to the Levi-Civita connection of the corresponding metrics. But this one has a metric, and this metric is curved. And the curvature of the metric, okay, these leaves are given by the condition that x3 is equal to constant, non-zero constant, and the curvature is really like this is the scalar curvature. So it's not even constant. And you can really see this example of symmetric Poisson structure describing some blow of the curvature as you approach this like 2-dimensional and 1-dimensional leaves. Along the sea, it explodes. Okay, I guess that's all for that 1 minute. I would like to just say a final remark. The final remark is that I told you something wrong intentionally, and it was the motivation. Because our motivation was not like doing Poisson, considering my geometry. Our motivation was generalized geometry, because in generalized geometry, everything starts with this guy. And when I arrived to Barcelona, Roberto told me, okay, take -0 and try to do generalized geometry with this guy. This naturally leads to the symmetric Poisson business. Thank you for this.
These examples are anticipated, but it's too clear. The example of the slides X3C is non-compact.
No, it's like topologically it's flat. It's right. It's just a time space. But the metric you're getting from theta is really curved because we calculate this established with a connection.
And the vector field doesn't depend on X3. It's another coordinate. It's not in direction X3.
Yes, that's correct.
And the Jordan, let's say Pascal Jordan.
Yes.
Yeah. And are they symmetric?
Yeah, these are like commutative algebra satisfying the type of the best.
So the octonion symmetric matrix is 3 times 3 belongs to that, the model of the Jordan. You find planes. This is the real connected radicality.
Okay, so I could be a bit if you can give me some reference. Because yeah, we kind of don't know much about all this symmetric part. It was kind of throughout us and deal with it.
What does it mean dimension is 5?
Well, dimension of the vector space is 5.
So the vector space.
Yeah, so the manifold is also 5-dimensional. It's 5-dimensional.
So it's different here. So it's not the same.
It's different here.
So it's not Jordan matrix, Jordan, Pascal, that's
Jordan. Yeah.
Because
Because it's the German.
Maybe I have a question. So can you view these symmetric Poisson structures as some kind of semi-classical limit of something that in the usual Poisson world would be a star product?
Yeah, so we kind of wanted to do something with star product, but then the answer was somehow that when you have a star product, you can somehow always scale the symmetric part or something. That's at least what I heard. So we didn't really open this direction.
Yeah, also,
But up to some equivalence, you can always scale the symmetric part.
sure, yes, this is true. No, my question was slightly different. So if you want to view the usual Poisson structures as the semi-classical limit of a star product, is there something else, more like a symmetric product maybe that is like a quantization of these structures that you have here?
Yeah. Well, it's kind of all related to somehow like Weil algebras, which can be seen as quantization of symmetric products. So this appears, for example, for this symmetric pairing. We have some algebra representation. And I guess that perhaps in this direction can do something. Maybe
Any more questions or remarks? Okay, then we can name the speaker again.